Hello everyone, welcome to another lecture of the course Digital Signal Processing. In the previous lectures, we had introduced the concept of discrete Fourier transform and we have seen the periodicity, modulo operation, the circular convolution for the DFT. Now, in this lecture, let us consider some important properties for discrete Fourier transform. And before that, let us get back to the analysis and synthesis equation for DFT. So this is the analysis equation, that is x of k, or n point DFT for a discrete time signal x of n, and this x of n can be reconstructed using this x of k using this synthesis equation given as 1 by n summation k running from 0 to n minus 1 x of k e to the power j 2 pi k n by n. And we know that the range of this k is from 0 to n minus 1 and the range of n is from 0 to n minus 1. So while discussing the properties of DFT, we are going to consider x of n has n point DFT as x of k. Similarly, we are going to consider another signal, that is x1 of n with n point DFT as x1 of k and x2 of n having its n point DFT as x2 of k, and we know that this x1 of k can be given as summation n running from 0 to n minus 1 x1 of n into e to the power minus j 2 pi k n by n, and this x2 of k can be given as summation n running from 0 to n minus 1 x2 of n into e to the power minus j 2 pi k n by n. So using these three things, we are going to consider different properties of DFT. So let us start with the first property, that is linearity property. We had seen that this x1 of n has the DFT as x1 of k and x2 of n has DFT as x2 of n. Now let us consider the linear combination of these two signals, that is, let us consider a into x1 of n plus b into x2 of n and find its DFT. Let's say it's given by x1 of k. So we have x1 of k is equal to summation n running from 0 to n minus 1. So our signal is a into x1 of n plus b into x2 of n into e to the power minus j 2 pi k n by n. So now we can just separate these two terms and we can write it as it is equal to, this a is constant so it can be taken outside, a into summation n running from 0 to n minus 1 x1 of n multiplied by e to the power minus j 2 pi k n by n plus b into summation n running from 0 to n minus 1 x2 of n into e to the power minus j 2 pi k n by n. Now this term here is the DFT for this x of n, which is x1 of k, and this summation here is the DFT for x2 of n, that is x2 of k. So we have x1 of k is equal to a into x1 of k plus b into x2 of k. Therefore what we have is, when we have a linear combination of signals in time domain, so we have linear combination in time domain, then its corresponding discrete Fourier transform is given as a into x1 of k plus b into x2 of k, and this is linear combination in frequency domain. And when we are considering this linear combination, the constants that we are getting, that is a and b here, are same, and this is known as the linearity property of discrete Fourier transform. So this is the linearity property. Now let us go ahead and check another property, which is the time reversal. So we have this x of n having its DFT as x of k. Now let us try to find out the DFT of x of the flipped version of n. That is, we need to find the circularly flipped version of x of n, its Fourier transform or discrete Fourier transform. So we need to find the DFT of this signal. Let's say it be given as x1 of k. So we have x1 of k is equal to summation n running from 0 to n minus 1 x of minus n modulo n e to the power minus j 2 pi k n by n. Now if we observe this term here, that is minus n modulo n, it can be represented as n minus n. For example, if we have the value of n equal to 4, and let's say my small n here is given by 3. So we need to find the value of minus n modulo n, which is equal to minus 3 modulo n, and it comes out to be 1. And if we consider n minus 3, or in simple words, if we consider 4 minus 3, so it is equal to 1. Therefore this modulo thing here can be represented simply by capital N minus 1. Therefore what we have is x1 of k is equal to summation n running from 0 to n minus 1 x of n minus n into e to the power minus j 2 pi k n by capital N. Now we will make a small substitution here and write m equal to n minus n. Therefore we have this n as n minus m, and the limits will now be, when we have n equal to 0, when we have n equal to 0, at that time the value of m would be equal to n, and when we have the value of n equal to n minus 1, at that time the value of m will be given as n minus n plus 1, so it is equal to 1. So what we have is x1 of k, it is equal to summation m running from 1 to n x of m e to the power minus j 2 pi k, inside the bracket it is n minus m by n. So we have x1 of k is equal to summation m running from 1 to n x of m into e to the power minus j 2 pi k n minus m by n. And now we can just split this term here into two complex exponentials. Moreover, the range of m from 1 to n can be simply considered from 0 to n minus 1, because this x of m is basically periodic in nature, and this periodicity we have obtained by discretization of the omega axis. So we can just change the limits here as summation m running from 0 to n minus 1 x of m into e to the power minus j 2 pi k n by n multiplied by e to the power minus j 2 pi, we can write it as minus k into m by capital N. And now this n gets cancelled here, and it is e to the power j 2 pi k, that is integer multiple of 2 pi. So this term here is equal to 1, and therefore we have summation m running from 0 to n minus 1 x of m e to the power minus j 2 pi into minus k into m by n. So this can be written as x of minus k, but now this minus k would be going outside the range of 0 to n minus 1, that is the range of k that we are considering, and therefore it has to be brought inside the range by considering the modulo operation. So this x1 of k can be written as x of minus k modulo n, or it can be also written as x of n minus k. Therefore, if we have the circularly flipped version of input, then the Fourier transform that we obtain, or the discrete Fourier transform that we obtain, is again a flipped version, that is x of minus k modulo n, or it can also be written as x of n minus n. N minus k, and this is known as the circularly flipping or circular flip property for discrete Fourier transform. Now let us move on to another property, and that is known as the circular time shift. So in this property, we are going to consider again x of n with discrete Fourier transform as x of k, and now we are going to circularly shift this x of n by L units. So we are going to make this x of n circularly shifted by L units. So we are going to get a modulo operator here due to circular shift, and now we need to find the value of this x1 of k. So we have x1 of k is equal to summation n running from 0 to n minus 1 x of n minus L modulo n e to the power minus j 2 pi k n by n. And now what we can do is we are going to consider this summation into two parts. So we are just going to split it into two parts like this. So we are going to consider this n as 0 to L minus 1 x of. Now when this n is ranging from 0 to L minus 1, so at that time this entire thing that is inside this bracket is going to be less than 0, and we know that when we have it less than 0, we can just write it as n plus this value, and therefore we can write this as n plus n minus L into e to the power minus j 2 pi kn by n, and we have the second summation as summation n running from 0 to n minus 1. So it would be n running from L to n minus 1, and at that time this bracket here would be having value from 0 to n minus 1 minus L, and at that time we are going to get the value of this bracket inside the range of 0 to n minus 1, and therefore this can be simply written as it is. So we have it as n minus L into e to the power minus j 2 pi kn by capital N. So we have x1 of k is equal to summation n running from 0 to L minus 1 x of n plus n minus L multiplied by e to the power minus j 2 pi kn by n plus summation n running from L to n minus 1 x of n minus L multiplied by e to the power minus j 2 pi kn by n. Now let us consider these two summations individually, so we can just write it as S1 plus S2. So let us consider this S1 first. So we have S1 is equal to summation n running from 0 to L minus 1 x of n plus n minus L multiplied by e to the power minus j 2 pi kn by n. Now let us substitute m equal to n plus n minus L. Now when we have n equal to 0, then value of m is equal to n minus L, and when we have the value of n is equal to L minus 1, at that time we have the value of m as n minus, so it is n plus L minus 1 minus L, which is equal to n minus 1. Therefore this summation S1 can be written as summation n running from 0, so it would be basically m running from n minus L to n minus 1 x of m into e to the power minus j 2 pi k by n, and the value of this n is to be substituted as m minus n minus L. Plus L. Therefore what we have is S1 is equal to summation m running from n minus L to n minus 1 x of m multiplied by e to the power minus j 2 pi k by n. Now if we observe this exponent here, we can split it into three complex exponentials, so it can be written as e to the power minus j 2 pi k m by n multiplied by e to the power minus j, so it would be plus j 2 pi k n by n multiplied by e to the power minus j 2 pi k l by n. Now this factor here is going to be 1 because this n and n will get cancelled, and we have e to the power j 2 pi k. Now this is again integer multiple of 2 pi, and therefore it will result into 1. So we are left with only these two terms. So we have e to the power minus j 2 pi k m by n multiplied by e to the power minus j 2 pi k l by n. So let us number this equation as 1. Now let us consider the second summation. So it is given as summation n running from L to n minus 1 x of n minus L e to the power minus j 2 pi kn by n. Now we are going to substitute this m as n minus L. Now when we do this, then the limits when n is equal to L, this m becomes 0, and when this n is equal to n minus 1, at that time the value of m becomes n minus L minus 1, and therefore this summation S2 now results into m running from 0 to n minus L minus 1 x of m multiplied by e to the power minus j 2 pi k by n. Inside the bracket it would be given as m plus L. Therefore this summation S2 can be written as summation m running from 0 to n minus L minus 1 x of m into e to the power. So this can be split into two parts, that is e to the power minus j 2 pi k m by n and e to the power minus j 2 pi k L by n. So we have e to the power minus j 2 pi k m by n multiplied by e to the power minus j 2 pi k L by n. And now let us number this as 2. And we know that the value of x1 of k is equal to S1 plus S2. So it can be written as summation m running from 0 to n minus L minus 1 x of m inside the bracket. So it is inside the bracket e to the power minus j 2 pi k m by n multiplied by e to the power minus j 2 pi k L by n plus summation m running from n minus L to n minus 1, and we have x of m into e to the power minus j 2 pi k m by n multiplied by e to the power minus j 2 pi k L by n. So now we can just take this factor common from both the summations. Moreover, if we observe the remaining part, then this limits can be considered together and both the summations can be combined into one factor. So it can be written as summation m running from 0 to n minus 1 x of m into e to the power minus j 2 pi k m by n multiplied by e to the power minus j 2 pi k L by n. Now if we observe this factor here, that is summation m running from 0 to n minus 1 x of m into e to the power minus j 2 pi k m by n. So this is nothing but the value of x of k, that is discrete Fourier transform of this x of m. Therefore this x1 of k is equal to dft of x of n multiplied by e to the power minus j 2 pi k L by n. So when we circularly shift x of n by a factor of L in the frequency domain, that is for the DFT of x of n gets simply scaled by this factor, that is e to the power minus j 2 pi k L by n. And this is the circular shift property in the time domain. Now if we go for circular shift in the frequency domain, that is if we shift the discrete Fourier transform circularly, that is k minus L mod n. So if we have x of k minus L modulo n, then the change in time domain is quite similar, that is the time domain signal x of n also is scaled by the complex exponential e to the power j 2 pi n L by n, but now with a positive sign. And this thing can be proved in a similar way as we have considered the circular shift in the time domain. So when we have a circular shift in the frequency domain, we are again going to get back a complex exponential scaling in the time domain, and we are again going to have this factor of L but with a positive sign. So now let us move ahead to another property, that is complex conjugate property in the time domain. That is, we have this x of n with dft as x of k. Now suppose we take the complex conjugate of this, that is x conjugate of n, then what is the value of this dft? Let's say x of k, x1 of k. So we have x1 of k as summation n running from 0 to n minus 1 x conjugate of n e to the power minus j 2 pi kn by n. Now let us take the complex conjugate of both LHS and RHS, that is find the value of x1 conjugate k, which is given as summation n running from 0 to n minus 1. So conjugate of conjugate would be the original signal, that is x of n, and this, if we take the complex conjugate of this factor, so we are going to get a sign change here. So we have j 2 pi kn by n. So this can be written as summation n running from 0 to n minus 1 x of n e to the power minus j 2 pi, we have minus k n by capital N. Now we know that this can be written as, this entire thing here can be written as x of minus k, but it would be a circular shift, so it would be x of minus k modulo n. Therefore what we have is x1 conjugate of k is equal to x of minus k modulo n, but we need to find the value of x1 of k, so let us again take the complex conjugate. So it would be x1 of k is equal to the complex conjugate of x of minus k modulo n. So when we consider complex conjugate in the time domain, that is x conjugate n, in the frequency domain we are again going to get conjugate but with a circular shift. So this is known as the complex conjugate property in the time domain. Now if we have complex conjugate in the frequency domain, that is if we consider the complex conjugate of this DFT, then similar to the time domain complex conjugate, we are going to get conjugate but with a circular shift in the time domain. So if we take the complex conjugate of the circularly flipped version of this x of n, then we are going to get complex conjugate in the frequency domain, and this is known as the complex conjugate property in the frequency domain. So let us move ahead to another property, so that is circular convolution, and we had already seen this property, that is if we have circular convolution of two signals, that is x1 of n and x2 of n in the time domain, then correspondingly we are going to get the multiplication of its corresponding discrete Fourier transform, that is x1 of k into x2 of k, and this is known as the circular convolution. Now if we have multiplication in time domain, that is if we have x1 of n multiplied by x2 of n, then what we'll be getting in time domain would be a circular convolution, that is but scaled by a factor of 1 by n, that is we are going to get 1 by n into x1 of k circularly convolved with x2 of k. So this is similar to the circular convolution in the time domain, that is when we are having convolution or circular convolution in the time domain, we get multiplication in the frequency domain, and similarly if we have multiplication in time domain, we are going to get circular convolution in the frequency domain but with a scaling factor of 1 by n. So this is the time multiplication property. Now if we go ahead, the next property is known as the circular convolution. And this circular convolution, what we have is, we have x1 of n having the DFT as x1 of k and x2 of n having DFT as x2 of k, and this circular convolution, say R, is given as, this circular correlation, that is R, is given as summation n running from 0 to n minus 1 x1 of n multiplied by x2 conjugate of n minus L modulo n. Now we know that this x1 of n has the Fourier transform as x1 of k, DFT as x1 of k. Now let us consider this factor here, that is x2 of n, that is here. So we have x2 conjugate of n minus L modulo n, and we know that this is a circular shift, but moreover, if we observe this factor here and observe this equation carefully, this can be written as x1 of n circularly convolved with x2 of the flipped version, that is minus of n modulo n. So it can be considered as the circular convolution of these two signals, and we know that this x1 of n has DFT as x1 of k. Moreover, using the flipping property, so we have a conjugate here. So using this conjugate property in the frequency domain, so this x conjugate minus n modulo n will be having the DFT as x2 conjugate of k. So we have taken this from the property here, that is, if we have x conjugate of minus n modulo n, then we are going to get conjugate in the frequency domain. So the DFT of x2 conjugate minus n modulo n would be simply x2 conjugate k. And therefore, we know that convolution in the time domain is simply multiplication in the frequency domain, and therefore this x1 of n circularly convolved with x2 conjugate of minus n modulo n, so it results into x1 of k, so it results into DFT of x1 of k multiplied by x2 of k, but this x2 of k is basically conjugate. So this is known as the circular correlation property for DFT. Now the other property or theorem is the Parseval's theorem. So this Parseval's theorem says that if we have a signal x1 of n and we have its DFT as x1 of k, similarly if we have a signal x2 of n and if we have its DFT as x2 of k, then summation n running from 0 to n minus 1 x1 of n multiplied by x2 conjugate of n will be equal to summation k running from 0 to n minus 1 x1 of k multiplied by x2 conjugate of k, but scaled by a factor of 1 by n. So now let us start with this left hand side in order to prove that. So we have the left hand side as summation n running from 0 to n minus 1 x1 of n multiplied by x2 conjugate of n, And we know that this x1 of n can be represented using the synthesis equation. So we have is equal to summation n running from 0 to n minus 1. So it is equal to 1 by n. x1 of n can be written as 1 by n summation k running from 0 to n minus 1 x1 of k into e to the power j 2 pi kn by n multiplied by x2 conjugate of n. Now what we can do is we can just take this summation here and take this entire part outside. So just rearranging the things, what we get is 1 by n summation k running from 0 to n minus 1 x1 of k multiplied by summation n running from 0 to n minus 1, it is x2 conjugate of n into e to the power j 2 pi kn by capital N. So what we have is this LHS is equal to 1 by n summation k running from 0 to n minus 1. We have x1 of k, then we have summation n running from 0 to n minus 1 x2 conjugate of n into e to the power j 2 pi kn by n. Now this entire term here can be written as summation n running from 0 to n minus 1 x2 of n into e to the power minus j 2 pi kn by n and its whole conjugate. And if we observe this factor inside this bracket, so it is simply the DFT of this x2 of n, that is x2 of k, and therefore this results in x2 conjugate of k, and therefore this LHS can be written as 1 by n summation k running from 0 to n minus 1 x1 of k into x2 conjugate of k, which is equal to the right hand side, and this is known as the Parseval's theorem. So in this lecture we have considered various properties of DFT, and we started with the linearity property, in which we saw that if we have linear combination in time domain, we are going to get linear combination in the frequency domain with same constants. The next property that we saw was the time reversal property, and we saw that if we have circular flipping in the time domain, then we are again going to get circular flipping in the frequency domain. So this is the circular flip property or time reversal property. The next property that we saw was circular shift in the time domain, that is if we shift the signal circularly in the time domain, then what we are going to get in frequency domain is simply multiplication by a factor, that is e to the power minus j 2 pi kl by n. So basically if we have a circular shift in the time domain, then we get the DFT, that is x of k, circular shift x of k scaled by a complex exponential e to the power minus j 2 pi kl by capital N. So we get this extra factor by introducing a circular shift. Then we saw that if we have circular shifting in the frequency domain, we again get a complex exponential in the time domain but with a positive sign. The next property was the complex conjugate property, and we saw that if we have complex conjugate of the time domain signal, we are going to get a complex conjugate in the frequency domain, but it would be circularly flipped. Similarly, if we have complex conjugate in the frequency domain, we obtain complex conjugate in time domain but circularly flipped. Further, we had already seen this circular convolution, so we just revised it that if we have circular convolution in time domain, we are going to get multiplication in the frequency domain. Similarly, if we have multiplication in time domain, we are going to get circular convolution in the frequency domain, but with a factor of 1 by n. The next property we saw was of circular correlation. So we saw that if we have circular correlation in the time domain, we are going to get multiplication, that is x1 of k into x2 of k, but this x2 of k will be conjugate. That is, circular convolution in time domain would be resulting in x1 of k into x2 conjugate of k. And then we saw what is the Parseval's theorem and saw that if we have two signals with endpoint DFT as x1 of k and x2 of k, and if we consider summation n running from 0 to n minus 1 x1 of n into x2 conjugate of n, then we are going to get 1 by n summation k running from 0 to n minus 1 x1 of k into x2 of k. So these two terms are exactly equal and we have already proved that. Now suppose we consider x2 of n equal to x1 of n, then at that point we are going to get summation n running from 0 to n minus 1, and it would be x1 of n into x2 into x1 conjugate of n. So it can be written as mod of x1 of n square, and it would be equal to 1 by n summation k running from 0 to n minus 1. Again we would be having x1 of k multiplied by x1 conjugate of k, and it can be written as x1 of k square. Now if we observe this is the energy in one period. Therefore we can find the energy using this formula or this formula. So if we have domain change, we are not going to have any harm with the energy. So this Parseval's theorem allows us to find the energy irrespective of the domain, and it says that the energy is not lost, or the energy in time domain is exactly equal to the energy in the frequency domain. So this is Parseval's theorem. In this next lecture we are going to revise these properties again in short. So let's stop here. Thank you.